Hey, welcome. Today we are going to dive into a mathematical game that's so simple you can play it on a napkin. But here's the catch. It has a secret pattern that has been puzzling people for over a century. I mean, what if you could take any four numbers, apply just one simple rule over and over again, and watch them tell a story that always, and I mean always, has the same magical ending? Well, that's exactly the idea behind this game. It's an old puzzle that came out of Italy, and it has this single, super easy rule. But the outcome? It's always a huge surprise the first time you see it. So, what is this game? It's officially called a Ducci sequence, and its story actually starts way back in Italy in the 1880s. So let's open up this puzzle box and see how it works. To get started, all you need is four numbers. Any four numbers will do. For our first game, let's use 40, 25, 33, and 52. As you can see, we've just placed them at the corners of a square. We're going to keep this diagram right here on the screen so you can follow along as we apply the one and only rule. So here's the rule. You just find the difference between each neighboring number. That's it. Just subtract the smaller one from the bigger one. So between 40 and 25, the difference is 15. Then, moving around the square, between 25 and 33, it's 8. Next up, the difference between 33 and 52 is 19, and to close the loop, the difference between 52 and our first number, 40, is 12. And just like that, we've got a brand new set of four numbers, 15, 8, 19, and 12. These become the corners of our next, slightly smaller square. So, what now? Well, we just do the exact same thing all over again. We just keep on repeating this process. Find the differences, make a new square, and go again. If you follow the diagram as it spirals inwards, you can actually see the numbers getting smaller with each step. And then, something pretty amazing happens. After just 4 steps with this set of numbers, we land on a square of all zeros. 0, 0, 0, 0. And that's it. Game over. So that's really all there is to it. You start with 4 numbers, you find the difference between the neighbors, those become your new set of 4 numbers, and then you just repeat. That's the whole game. And the wildest part is, no matter what numbers you start with, you will always eventually end up at all zeros. Okay, so this brings up a really interesting question, right? How long does a game usually take? Does it always wrap up in just a few steps like that one did? In the world of these Ducci sequences, this is what's known as the length of the game. It's literally just the number of steps it takes for the 4 numbers to hit all zeros for the very first time. So our first example game had a length of 4. But is a length of 4, typical? Or can these games sometimes go on for way, way longer? Oh yeah, they can go longer, a lot longer. Take a look at this monster. If you start with the numbers 15, 158, 15, 915, and 425, the game takes a mind-boggling 15 steps to finish. I mean, you can just see how much crazier that nested diagram gets. And that's not the only one. Researchers have used computers to hunt for these super long games. They found one that starts with 812, 549, 64, and 956 that takes 16 steps. And you can see a few others here that take 14 or 15 steps, so these long games are definitely out there. So this kind of raises a bigger question. We've seen a game that takes 4 steps and one that takes 16. What does a typical game actually look like? Are these super long games super rare, or are they common? Yeah, this is the big mystery, isn't it? Are we just as likely to stumble upon a game that lasts 15 steps as we are to find one that lasts 4? Or are these long games like finding a needle in a haystack? Well, to figure this out, we can just run a simulation. Play thousands and thousands of games with random numbers, and then just plot the results. And what we get is this chart showing us how often each game length pops up. And when you look at all that data, a really clear pattern just jumps out. Do you see that huge spike right there at the number 4? It turns out it doesn't matter what numbers you test, you find the exact same thing. About half, 50%, of all games you could possibly play have a length of exactly 4. But wait, this brings up another obvious question. You'd think, intuitively, that starting with really big numbers, like numbers in the thousands, would make the games last longer than starting with small numbers, right? I mean, it seems like it should, but does it? And this right here is one of the game's biggest and coolest surprises. Seriously. On the left, that's the pattern for numbers between 0 and 10. On the right, it's for numbers all the way up to 10,000. And look at them, they're almost identical. It's wild. The size of the numbers you start with has almost no impact on how long the game lasts. That 50% chance of a four-step game is true whether your numbers are tiny or gigantic. So what are we supposed to make of all this? We've got a game with rules so simple a kid could play it, but it has patterns hidden inside that are so deep they can still surprise mathematicians. There's a quote from one of the papers about this that just sums it up perfectly. With its simplicity, beauty, and mathematical richness, the four-number game is truly one of the classic mathematical curiosities. And that's really why this little game is so important. It's a perfect example of how really simple rules can create incredibly complex and fascinating behavior. It's like a fun open door into the world of math and patterns that anybody can walk through. And it just reminds us that you don't need complicated formulas to find amazing things. Sometimes all it takes is a little bit of curiosity. And the best part, you can grab a piece of paper and try it yourself right now. It really makes you wonder, doesn't it? If a puzzle this simple can hold so many secrets, what other beautiful patterns are just hiding out there, in plain sight, waiting for someone to get curious and find them?